A little progress each day adds up to big results. Hi everyone. In this video we'll go through types of relations and few problems. This is the first video of this particular chapter. You can refer relations and functions playlist for videos specific to this chapter or class 12 mathematics playlist which has all the videos specific to mathematics. So before we jump into the problem, let's recall the types of relations. So there are three types of relations mainly: reflexive, transitive and symmetric. So what is a reflexive relation? Say you have a set A which has elements 1, 2, 3, and then you have relation R which is a set of ordered pairs, right? And the elements in these ordered pairs belong to this particular set A, right? Now if you have ordered pairs where first element and second element is same, like this 1, 1, 2, 2, 3, 3. So for every element of set A, you should have ordered pair where first element and second element are same. So you have 1 here, so you should have 1, 1. You have 2 here, so you should have 2, 2. You have 3 here, so you should have 3, 3. So if there is a relation R where for every element of set A belongs to R. That is, for every element in set A, you have the element and its mirror image. You can call this as mirror image, right? 1, 1, 2, 2. You can call it as mirror image. So for every first element, if you have the same second element, and this should happen for all the elements of set A, then the relation R on set A is called as reflexive. Then the relation R on set A is called as reflexive relation. Now let's take an example. Let me modify this example. Let me put number 4 also in this particular set. Right? Now, would you call this relation reflexive? No. This relation is not reflexive. Why? Why? Because you have 4 and you should have 4, 4. You should have 4, 4, which is not there in this particular relation set. That's why this becomes not reflexive. Now, if I put 4, 4 also here, say I put 4, 4 also in this particular relation, then this becomes reflexive. Reflexive because there are 4 elements in A, and for all the 4 elements you have ordered pairs in relation, right, where the first element and second element are same: 2, 2, 3, 3, 4, 4, 1, 1. So what is the definition? A relation R on a non-empty set. So set A should be non-empty. That means set A should have some elements, at least one element. So a relation R on a non-empty set A is called a reflexive relation if A, A. So you assume that A is the element that belongs to set A. So A, A is, you should have same element and that should belong to R. Relation R. That's when you say that R has a relation on A and the relationship is reflexive. Now this relationship is reflexive. Now let's go to the second type of relation, symmetric relation. Now what is a symmetric relation? So let's assume that we have set A which is 1, 2, 3, 4, 5. Right? These are the elements in set A. 1, 2, 3, 4, 5. Let's consider that this is relation R1, right? It has these ordered pairs, right? It has these ordered pairs. So the condition for a relation to be symmetric, if a relation on set A has to be symmetric, right? If there has to be a relation from R1 to A, and if that relationship is symmetric, then the condition is whatever ordered pairs you have in R1, So for example, if you take this first ordered pair, you have 2 comma 3. If you have 2 comma 3, then the reverse combination also should be there, that is 3 comma 2. And if you have 3 comma 4, then the reverse combination is 4 comma 3. For every ordered pair in relation, there has to be a reverse arrangement of the ordered pair also. So first element, second element should get exchanged in the next order pair, right? So you have 2 comma 3 and it gets exchanged. It becomes 3 comma 2 in the next ordered pair. Here it's 3 comma 4 and then it becomes 4 comma 3. So if you have such kind of a relation, then it's called a symmetric relation. You can say that R1 has a symmetric relation on set A. So what is the definition? A relation R on a non-empty set A, is called a symmetric relation if A comma B belongs to R, that is you have an ordered pair. You can generalize this as A comma B. If this belongs to R, this implies or means, right? Anything. This implies or this means that B comma A should belong to R. B comma A. So the second element and the first element will get swapped. Now let's take this particular example. R2 is equal to, you have these ordered pairs. Now let's figure out if this is symmetric or not. You take the first ordered pair. So you take the first ordered pair 1 comma 5. So what should happen? This should get reversed. It should become 5 comma 1. So it is there. Then you have 2 5. So you should have 5 comma 2. So it's there. So this is symmetric. This is symmetric relation. Now let's take the third one. R3. So you have these ordered pairs. You have 2 comma 3. So we should have 3 comma 2. This is there. Here you have 3 comma 4. But we don't have 4 comma 3. Right? So this is not symmetric. This is not symmetric. Another example. Here we have 1 comma 5. The opposite of this is 5 comma 1. 5 comma 1 is not there in this set. So this is also not symmetric. Now let's go to transitive relation. What is a transitive relation? So you have the set A. See, it has 5 elements. 1, 2, 3, 4, 5. Right? Now transitive states that if you have 1 comma 2 in relation and you have 2 comma 3, then you should also have 1 comma 3. Now what it means? So notice this. You have 1 comma 2 and 2 comma 3. So the second element in this first pair and the first element in the second pair should be same. So you have this 2 and 2 as same. So now you have 2 comma 3 here. So what should be the third pair? You should have this first element and the last element 1 comma 3. So this is what is a transitive relation. That is, if A comma B and B comma C, notice here B and B are same. So if A comma B and B comma C both are present in relation R, then you should have A comma C also in R. Then you should have A comma C also in R. That is first and the last element. First element and the last element should be present in R. That's when you say it's transitive. Now there is also one more thing that we'll have to be careful. Sometimes you have 1 comma 2 but you will not have 2 comma 3. Right? Say for example, I'll modify this. I'll remove this. Right? Now in this, I say let this be the relation. I have only 2 ordered pairs 1 comma 2 and 1 comma 3. Now would this be transitive or not? This would be transitive. This would be transitive because you have 1 comma 2. Ideally you should have another second element and something else, like something like else, right? Ideally you should have same second element here 2 and something else. So here you don't have 2 comma 4 or 2 comma 3 or anything, right? Because of that, you can call this as transitive. So if you are not able to get this combination b comma c, right, in the relation, if you are not able to get this combination b comma c, then you can call it as transitive. Because we cannot prove that it is not transitive. We cannot prove, because unless this pair is there, you can't prove. But since the pair itself is not there, this pair itself is not there, b comma c, you can call this as transitive relation. So now this becomes transitive. Let's take another example. So here you have 2 comma 4, you have 4 comma 2. Now you have both. If you take this as a comma b and b comma c, then you should have a comma c. That is, this is a and this is c, the first and the fourth element. So we should have 2 comma 2. Do we have 2 comma 2 here? No, we don't have 2 comma 2. So this is not transitive. So this is not transitive. Now what is an equivalence relation? A relation which is reflexive, symmetric and transitive. So if the relation is reflexive, symmetric and transitive, that is all three types of relations are satisfied, then you can call that relation as equivalence relation. So now let's get into the problems. The first one is determine whether each of the following are reflexive, symmetric and transitive. You have set A, which goes from 1, 2, 3, 4, 12, 13, 14. So there are 14 numbers in set A. And what is the relation? R is equal to R as ordered pairs x and y, where 3x minus y is 0. This means R is equal to xy. I know x. I can take x from this set A. What will be y? Y is given by this particular equation. So what does this mean? Y is equal to minus y is equal to 0 minus 3x. Therefore, y is equal to 3x. So this is the value of y. Basically, y is 3 times of x. So y is equal to 3 times of x. So now let me first form a relation. Let me get all the ordered pairs in the relation, right? To figure out if it's reflexive, symmetric or transitive, I should first have the ordered pairs in the relation, right? Let me form the relation. So I'll take the first element 1. Y should be 3 times of x. So if x is 1, y should be 3 times of x. That is, x is 1. So it's 3, right? 1 comma 3. X is 1 and y is 3 times of x, 3 into x. So if x is 1, y is equal to 3 into 1, which is 3. So 1 comma 3. Now next one would be, I'll take x as 2. If x is 2, then y is 3 times of x, that is 6. Next I'll take x as 3. So y will be 3 times of x, 3 times of 3, which is 9. Similarly 4. 3 times of 4 is 12. Now I'll take the fifth element 5. 3 times of 5 is 15. Now carefully observe, is 15 part of this particular set A? No. So you should always get the ordered pairs in such a way that both the elements x and y belong to set A. So here if you see, 15 does not belong to the set, right? 15 does not belong to the set. So this is not a valid ordered pair. The set ends here. The set ends here. Because if you continue, you will not get the elements. So if I take 6, 3 times of 6 is 18. 18 is still not present in this. If I take 7, 3 times of 7 is 21. 21 is not present in this, right? So we'll stop it here. Now we have the relation. Let's find out if it's reflexive. So if it has to be reflexive, what is the condition? A comma A should belong to relation R. A comma A should belong to relation for every, this is for all or every element that belongs to set A, right? So set A is given here. For every element of this set A, you should have A comma A, right? So if I take 1 year, set A as 1 year, do I have 1 comma 1 here? Do I have 1 comma 1? No. 2 comma 2? No. So therefore this is not reflexive. Now we'll go through second type of relation, that is symmetric. Is it symmetric? What is the condition for symmetric? If A comma B belongs to R, this implies that B comma A should also belong to R. So now let's look at the ordered pairs in relation. Here 1 comma 3. If 1 comma 3 is there, then you should have the reverse combination, which is 3 comma 1. Is 3 comma 1 there? No. Since 3 comma 1 is not there, this is not symmetric. Now we'll check if this is transitive, right? We will check if this relation is transitive. What is the condition? If A comma B belongs to R and B comma C belongs to R, then A comma C should also belong to R, right? If this condition is satisfied, then you can call it as transitive. You take the first ordered pair, 1 comma 3. If you look at the common element, the second element you should have some common element here. Here you have 3. Now 1 comma 3, 3 comma 9 means you should have 1 comma 9, right? Second element here and first element here is same. So first and fourth element should be present. First and fourth element. First element and fourth element. That is 1 comma 9. 1 comma 9 should be present. Is it present here? No. Therefore, this is not transitive. Not transitive. So the way you should write the answer is, for reflexive, you can say 1 comma 1, 2 comma 2, 3 comma 3 are not present in R. Therefore, R is not reflexive. This is one way of writing. The other way of writing is A comma A does not belong to R for all A belonging to set A. This is another way of writing. Therefore, R is not reflexive. Right? You can either write it this way or this way. Now, for symmetric, how will you write? You'll write AB belongs to R implies that BA belongs to R, right? But here, BA does not belong to R. So, it does not imply, right? AB belongs to R does not imply that BA belongs to R, right? This example. 1, 3 belongs to R. You can write example. 1, 3 belongs to R, but 3, 1 does not belong to R. Therefore, R is not symmetric. So, you can either write it like this or you can write it with an example, making it more clear. Now, for transitive, how do you write? You can write it like this. AB belongs to R, BC belongs to R, but AC does not belong to R. So, example, 1 comma 3 belongs to R, 3 comma 9 belongs to R, but 1 comma 9 does not belong to R. This symbol indicates does not belong to R. Therefore, R is not transitive. Now let's take the second example. Relation R in the set n of natural numbers defined as y is equal to x plus y and x less than 4. Now, the set is n and this set of natural numbers. What is natural numbers? Numbers starting from 1 goes till infinity, right? That is all positive numbers. Only positive numbers starting 1 till infinity is natural numbers. It does not have 0. Okay, it does not have 0 because 0 is not a natural number. It does not have 0 in this. Okay, so now this is the set. Now what is the relation given here? Relation is you have ordered pair xy where x is less than 4 and y is equal to x plus 5. So this is the relation. Now let's first form relation with some ordered pairs. Let's first find that. So r is equal to x is less than 4. So I can take 1, 2, 3, right? I can take set with 1, 2 and 3. It cannot be equal to 4 or it can't be greater than 4. It should always be less than 4. So now you have 3 ordered pairs basically. Now we need to find the second element. What is the second element? It's given by this equation, x plus 5. So you add 5 to the x. So 5, so you add 5 to x. So 5 plus 1 is 6, 5 plus 2 is 7, 5 plus 3 is 8. So this is the relation. Now we'll have to find out if this is reflexive, symmetric and transitive. So first one is reflexive. So what is the condition for reflexive? For every element A belonging to set n, in this case it's this set n, A comma A should belong to R. This is the condition for reflexive. For every element that belongs to natural numbers, A comma A should belong to R. Now here you have 1. So you should have 1 comma 1. Do we have 1 comma 1 here? No. Right? 1 comma 1 is not there. So 1 comma 1 does not belong to R. Right? Therefore, you can say A comma A does not belong to R and therefore R is not reflexive. R is not reflexive. You don't have 1 comma 1, 2 comma 2, 3 comma 3. Therefore R is not reflexive. Now we'll figure out symmetric. Now what is the condition for symmetric? If AB belongs to R, this should imply that B comma A also belongs to R. That is, the reverse combination should be there in R. Now let's go and check out. We have 1 comma 6. We don't have 6 comma 1. We have 2 comma 7. We don't have 7 comma 2. The reverse combination is not there. Right? The reverse combination is not there. Therefore, you can say example 1 comma 6 belongs to R, but 6 comma 1 does not belong to R. Therefore, R is not symmetric. Or you can also write, since AB belongs to R and BA does not belong to R, AB belongs to R, but BA does not belong to R, you can say R is not symmetric. The next one is transitive. What is the condition for transitive? If A comma B belongs to R and B comma C belongs to R, then it implies that first element and fourth element, that is A comma C belongs to R. Now we should check if this condition is applicable. So A comma B belongs to R. So you have only these three ordered pairs, 1 comma 6, 2 comma 7 and 3 comma 8. If you notice the second element 6 here, right? But you don't have any ordered pair with starting with 6. And here also second element is 7. You don't have any ordered pair starting with 7. So you cannot validate at all, right? This B comma C does not exist in R. B comma C does not exist in R. Therefore, you will not call it not transitive. You will say it is transitive. Therefore, it is transitive because you cannot validate. You cannot figure out. Since you cannot figure out, you cannot conclude that this is not transitive. So you will say this is transitive because you cannot verify. Because B comma C is not there at all in that list. Therefore, since you cannot verify, you should write A comma B belongs to R, but B comma C does not belong to R. Therefore, R is transitive. This is very important. Because B comma C does not belong to R, that is, you don't have 6 comma something or 7 comma something or 8 comma something. Since this does not exist, you say R is transitive. Now, I'll modify this slightly. I'll just modify this slightly. Instead of 2, say I have 6 comma 7. Just for example, say I have 6 comma 7. Now I can validate because 1 comma 6 is there, 6 comma 7 is there. Now based on transitive, what should I have? I should have 1 comma 7. I should have 1 comma 7 here. So since I have 1 comma 6 and 6 comma 7, I should have 1 comma 7. That is the first element, and the fourth element should be there in the ordered pair. But 1 comma 7 is not there. So in this case, I would call it as not transitive. In this case, I'll call it as not transitive. So I hope this difference is clear, right? I hope this difference is clear. So let's take another example. Relation R in the set A has 1, 2, 3, 4, 5, 6. And the relation is y is divisible by x, right? So you have a set with elements from 1 to 6. Then the relation is defined as y is divisible by x. So basically, R has all ordered pairs where y, that is second element, is divisible by first element. So for example, you can say 4 is divisible by 2. And 4 and 2 both should belong to A, right? Set A. The elements, the second element and the first element should belong to set A. Now let's first figure out if it's reflexive. So what does reflexive state? It states that for every element A belonging to A, that for every element in this set A should be divisible by A. That means here y is divisible by x. Y is second element, but in reflexive case, second element and first element should be same thing, right? So that means x and x. That means x is divisible by x, right? Or A is divisible by A. Now here I can consider first element, say 1. Is 1 divisible by 1? Yes, right? 1 is divisible by 1. 1 by 1 is 1. Similarly, I'll take number, second element 2. Is 2 divisible by 2? 2 by 2, it's divisible, right? Then is 3 divisible by 3? Yes, 3 is divisible by 3. So that way, every element is divisible by itself, right? So you can say, since for all A that belongs to A comma A belongs to R. That is nothing but, you can also say, for every element A that belongs to A, you can write it as x because they've given x here. They've given in terms of xy, so we'll put x. For every element x belonging to set A, x is divisible by x. Therefore, R is reflexive because x is divisible by x. Second element is divisible by the first element. In this case, both are same for reflexive. Now let's take symmetric. What is the condition? For every pair A comma B that belongs to R, B comma A should also belong to R. This is the condition, right? So now we will see. We'll go back to relation. Relation is y is divisible by x, right? Now, for example, if I take 4 is divisible by 2. 4 and 2 are present in this set A. So I'll take 4 and 2. 4 is divisible by 2. Does that mean for symmetric it should be reversed? 2 is divisible by 4. Right? If 4 is divisible by 2, does it mean that 2 is divisible by 4? No. Right? Because I can say 4 is divisible by 2. Right? But 2 is not divisible by 4. This will become half. It will become 0.5. Right? And here you get 2. You get the whole number as the answer. But here you get in decimal. This means that it is not divisible. It's not divisible. So whenever you get a decimal point, it means it's not divisible. Right? Simple. So here if you take 4 divisible by 2, you get the answer as 2. But here if you take 2 divisible by 4, you'll get 0.5, which is a decimal. And that's why it's not divisible. I'll take this an example. 4 is divisible by 2, but 2 is not divisible by 4. 2 is not divisible by 4. Hence, R is not symmetric. Right? How should I write? I can also write it as, for every pair AB belonging to R, BA does not belong to R. Or I can say XY belongs to R, but YX does not belong to R. Therefore, R is not symmetric. You can write it this way also. So you can take an example and say that R is not symmetric, or you can write in this format. XY belongs to R, but YX does not belong to R. Hence, R is not symmetric. See, this way also you can write. Y is divisible by X, but X is not divisible by Y. Hence, R is not symmetric. You can write it this way also. Right? Now let's look at transitive. Right? What is the condition for transitive? If XY belongs to R and YZ belongs to R, then first and fourth element, that is XZ, should belong to R. This is when it is transitive. Now here what is the relation? Y is divisible by X. So what should I say? Y is divisible by X. That's what they've told. Y is divisible by X. That's a relation. If Y is divisible by X and Z is divisible by Y, look at this. Look at this statement. If Y is divisible by X and Z is divisible by Y, then X is divisible by Z. Now what is the relation here? Relation is Y is divisible by X. If Y is divisible by X and what is the second case? Z is divisible by X. And if Z is divisible by Y, then what is this combination? X comma Z. Then Z is divisible by X. So here you have, in this case, first one, Y is divisible by X. Second one, Z is divisible by Y. Z is divisible by Y. Therefore, Z is divisible by X. Now, let's take an example. So, let's take X as 4. So, can I say 4 is divisible by 2? That is 4 by 2. Yes, 4 by 2 is 2. It's a whole number. It's a whole number. That means it is divisible. 4 is divisible by 2. Now next one is we need to find out z. Let's say z is equal to 8. Then 8 should be divisible by y. What is y? 4. Is 8 divisible by 4? Yes, right? 8 divided by 4 is equal to 2. Again, it's a whole number. Therefore, it is divisible. Now, second condition is satisfied. Let's look at third condition. Z is divisible by x. What is z here? 8. 8 divisible by 8 should be divisible by x. That is 2. Right? That is 2. 8 is divisible by 2. 8 by 2 is 4. It's a whole number. Therefore, it is divisible. So, using this example, we can say that R is transitive. Right? Using this example, we can say R is transitive, or we can say since y is divisible by x and z is divisible by y, z is divisible by x. Therefore, R is transitive. Or you can simply say x comma y belongs to R, y comma z belongs to R. Therefore, x comma z belongs to R. Therefore, R is transitive. You can simply write this particular statement. So here, in this particular example, R is reflexive, R is not symmetric, but R is transitive. So you should write R is reflexive, transitive, but not symmetric. Now let's take this particular example. Relation R in the set Z. Z is set of all integers. Integers are numbers from 0 to infinity. It can have both plus and minus, right? Both positive and negative numbers. Plus 1, minus 1, plus 2, minus 2, plus 3, minus 3. But it will not have decimal numbers. It will be whole numbers, right? Integers are always whole numbers, right? They don't have decimal in them. They don't have decimals, right? So that's what is integer. Now, you have Z, which is a set of all integers. The relation given is x minus y is an integer. X minus y is an integer. Now, let's look at reflexive condition. For reflexive, both first element and second element has to be same. So, here x minus y, we have x minus y is an integer. This is the relation, right? So, instead of y, I'll put x itself, right? Instead of y, I'll put x itself. So, x minus x is an integer. Is this true? X minus x is equal to 0, right? X minus x is 0 and 0 is part of the set Z. 0 belongs to Z. Therefore, this is reflexive. So, you should say x minus x is equal to 0 and this belongs to Z. Therefore, R is reflexive. So, now let's look at symmetric condition. For symmetric, if x minus y belongs to R, then y minus x, that is reverse it, right? Y minus x should belong to R and it should also belong to integer, right? Whatever answer you get out of this equation, it should belong to this set of integers. So let's take an example. If I take x as 2 and y as 3, so it will become 2 minus 3. 2 minus 3 is minus 1. Minus 1 belongs to Z, right? Minus 1 belongs to Z. Now I'll swap it, right? Instead of x I'll put y and instead of y I'll put x. So 3 minus 2. So 3 minus 2 is 1. Again 1 also belongs to Z, right? So therefore R is symmetric. So how do I write it? X minus y belongs to R implies that y minus x also belongs to R. Therefore, R is symmetric. Or I can say x minus y is an integer. This implies that y minus x is also an integer. That is the relation here. Relation is x minus y should be an integer. So x minus y is an integer, y minus x is also an integer. Therefore R is symmetric. Now let's look at transitive case. So for transitive case, we should have a combination like this. If x and y belongs to R and y and z belongs to R, then first and fourth element, that is x comma z should belong to R. Then we say R is transitive. Now here, let's take this x, y, y, z, zx combination. So what is the relation? X minus y should belong to z. Now if x minus y belong to z, then I'll take yz combination. Then y minus z belongs to z, which implies that first element x and last element z, x minus z belongs to z. This is true, right? Now let's take an example and figure out. If I take x as 2 and y as 3, right? X as 2 and y as 3, I'll get 2 minus 3 is equal to minus 1, which belongs to z. Now next is yz combination. This is x, this is y. So I'll take y and z as 4. So 3 minus 4 is minus 1. Now what should happen? Xz combination, right? X is 2 and z is 4. X is 2, right? X is 2 and z is 4, right? So 2 minus 4 is minus 2, which belongs to z. So now if you take an example also, you can prove that the relation is true. All these three are true, right? Therefore, you can say R is transitive. You can write it in this format, or you can put this example and say, since x minus y belongs to z and y minus z belongs to z, can imply that x minus z belongs to z. Therefore, R is transitive, right? You can also take this example and say, since 2 minus 3 belongs to z and 3 minus 4 belongs to z, therefore 2 minus 4 also belongs to z. Therefore, R is transitive. Now, this is an equivalence relation. Why? In this case, we saw that R is reflexive, R is symmetric, and R is also transitive. Since R is reflexive, symmetric, and transitive, we can call this an equivalence relation. Now let's go to another example. Relation R in a set A of human beings. So set A is a set of human beings in a town at a particular time, in a town. So what is the relation? X and Y work at the same place. X and Y work at the same place. And what are X and Y here? They are human beings, right? So you have set A, which is set of human beings, right? And the relation is all these human beings work at the same place. They work at the same place, right? So that is what we'll have to figure out if it's symmetric, transitive, and reflexive. Now, for reflexive, what should it be? The same element, x comma x. If x comma x belongs to R, for all, right? For all x that belongs to A, right? For every element in this set A, x comma x should belong to R, right? Now, for all human beings in this set, all the human beings, they should work in the same locality, right? So, x comma x belongs to R because x and x work at the same place, right? X and x can work at the same place. Therefore, this relation is reflexive. Symmetric. If xy belong to R, what is the condition? If xy belongs to R, and yx belongs to R, then you can call it a symmetry. The reverse. If xy belongs to R and yx belongs to R, then you can call it a symmetric. Now, it's simple, right? Let's take this example. You have x and y. X and y is Ram and Shyam, right? So, if Ram and Shyam work in the same locality, they work in same locality. Ram and Shyam work in same locality. So for symmetric, it should be y comma x. That is Sham and Ram. I am reversing it. Sham and Ram work in same locality. Does it matter if I change the positions? So if Ram and Sham work in same locality, we can also say that Sham and Ram work in the same locality, right? I can reverse the names. It doesn't make any difference, right? So this condition is true. I can say since xy belongs to R and yx belongs to R is symmetric. You can take this example and prove it. Now for transitive, what is the condition? If xy belongs to R and yz belongs to R, then xz should belong to R. The first element and fourth element should belong to R. Now we'll take an example. If Ram and Sham work in Bangalore, same locality, right? Say this is x, this is y. If x and y work in Bangalore, then I should take y and z. Sham and z, let z be Sita. If y and z work in Bangalore, say y and z also work in Bangalore, then can I say Ram and Sita, that is x and z, right? X and z. Can I say Ram and Sita work in Bangalore? Correct, right? If Ram and Sham work in Bangalore and Sham and Sita work in Bangalore, it means all three work in Bangalore, right? All three work in Bangalore. So it also means that x and z, that is Ram and Sita, work in Bangalore. Therefore, this is transitive. This is just an example to explain, but it's enough if you say if xy belongs to R and yz belongs to R, then xz belongs to R. Or you can write it as if x and y work at same place and y and z work at same place, then it means that x and z also work at the same place. Therefore, R is transitive, right? In both of these forms you can write. This is just an example. The next one. Here the relation is given as x and y live in the same locality. Exactly the problem is same, right? Here it was working in the same locality. Here it is living in the same locality. Same thing. So R is reflexive because x comma x, right? Right? The same person can live in the same locality, right? So x comma x belongs to R. Symmetric. So if Ram and Sham live in MG Road, Sham and Ram live in MG Road. This reverse is also true. Ram and Sham live in MG Road. I can reverse it. Sham and Ram live in MG Road, right? So if x and y live in MG Road, y and x also live in MG Road. Therefore, this is symmetric. Now transitive. This is also transitive. Same like the earlier example. xy belongs to R and yz belongs to R. It indicates that xz belongs to R. That is, you should write it like this, similar to this. If x and y live in the same place and y and z live, in that example it should be live in the same place, then x and z live in the same place. Now, let's look at this particular relation. X is exactly 7 cm taller than y. X is exactly 7 cm taller than y. This is very important. 7 cm. Right? This makes a difference, big difference. Now, let's see if this is reflexive. So, x comma x should belong to R. Right? That's the condition. X comma x should belong to R. That is, x should be 7 cm taller than x. Right? Instead of y, I'll have x for reflexive. X is exactly 7 cm taller than x. That's what it means. So instead of y, I'm putting x. X comma x. So x is exactly 7 cm taller than x. Can I be taller to myself? No, right? I can't be taller to myself. Right? Therefore, this is not reflexive. Therefore, I am telling x comma x does not belong to R and therefore R is not reflexive. You can write it like this. Next, symmetric. For symmetric, if x is 7 cm taller than y, then for symmetric I should reverse it. Right? It should become y is taller than x. If x is 7 cm, if x is 7 cm taller than y, is y 7 cm taller than x? That's not possible. Right? If x is 7 cm taller than y, can y be taller? No, y will be shorter. Right? It will not be taller. Therefore, this is not symmetric. So you should write it as xy belongs to R, but yx does not belong to R, right? You can write it as does not imply. xy belongs to R does not mean that yx belongs to R. Does not mean. This is does not imply. Does not imply. Right? I can write it like this. xy belongs to R. It does not imply that yx belongs to R. Therefore, R is not symmetric. R is not symmetric. I can also write this as R is not symmetric because x is 7 cm taller than y does not mean that y is 7 cm taller than x. Now let's look at the transitive case. Here, you should take x, y, y, z and x, z. This is the combination. If x is 7 cm taller than y and if y is 7 cm taller than z, it does not mean that x is 7 cm taller than z. It's like this. Now let's take Ram, Sham and Sita, right? Let's take 3 people here. So Ram is 7 cm taller than Sham. Ram is 7 cm taller than Sham. And Sham is 7 cm taller than Sita, right? Now does it mean Ram is 7 cm taller than Sita? No, Ram will be 14 cm. 7 cm taller than Sham and Sham is 7 cm taller than Sita. So it's going to be 14 cm. 14 cm. It's not going to be 7 cm. Therefore, it's not transitive. Because of this number, it's not transitive. If it was simply, if 7 cm was not there, if it was simply taller, right? Instead of, in the question, if 7 cm was not there, assume in the question, if 7 cm was not there, then the answer would be completely different. If x is taller than y and y is taller than z, that means x is taller than z, right? If Ram is taller than Sham and Sham is taller than Sita, it means Ram is taller than Sita, right? Ram is taller than Sita. So in this case, it becomes transitive. So the 7 cm is what is making a difference in the question. Since there is 7 cm, this is becoming not transitive. If it was simply taller without any number, then it would have been transitive. Now in this case, it is not transitive. So this relation is neither reflexive nor symmetric nor transitive, right? Not reflexive, not transitive and not symmetric. None of them. Now let's take this example. Your relation is x is a wife of y. Very simple, right? If x is a wife of y, y becomes the husband of x, right? Now let's take reflexive case. Here instead of y, I should put x, right? Can x be a wife of x? No, x cannot be a wife of x. So it's not reflexive. So it's not reflexive because x cannot be wife of x. Therefore, x comma x does not belong to R because x cannot be wife of x. So R is not reflexive. Now symmetric. In symmetric, what should happen? X and y, if x is a wife of y, then is y the wife of x? You have to reverse it, right? If x is the wife of y, is y the wife of x? No, that's not true. If x is wife of y, then y is husband of x. It's husband of x. So this is not true. Therefore, it's not symmetric. So you should write it this way. It's not symmetric because if x is wife of y, does not mean or does not imply that y is a wife of x, right? Or you can say xy belongs to R does not imply that yx belongs to R. Now transitive. If x is a wife of y, what is the next condition? Y is wife of z. Can it be possible? If x is wife of y, can y be wife of z? It's not at all possible, right? If Sita, for example, if Sita is wife of Ram, can Ram be wife of somebody? It's not possible, right? No, Ram cannot be wife at all. Ram can only be husband, right? Ram can only be husband. So in this case, I can't even take the second case. The second case does not exist. I cannot prove because the second case, that is YZ case, does not exist here, right? Therefore, this becomes transitive, right? Because I cannot prove that it is not transitive. I cannot verify at all because this YZ combination is not there. Therefore, R is transitive here. Let's take this example. X is father of Y, similar to the earlier problem itself. For reflexive, I'll replace Y with X, right? Y with X. So can X be a father of X? Can X be a father of himself? No, right? It's not possible at all. Therefore, it's not reflexive. Symmetric. If X is a father of Y, then is Y a father of X? It cannot be reversed, right? Right? It's not possible. So I can say XY belongs to R does not imply that YX belongs to R. Therefore, R is not symmetric. Transitive, same thing. It will not be transitive because if X is a father of Y, X is a father of Y and Y is a father of Z, then can I say X is father of Z? That's not possible, right? If X is father of Y and Y is father of somebody else, how can X be father of Z? How can X be father of Z? That's not possible. So it's not transitive. See, there is a difference between the earlier problem and this problem. There, the second case, Y is a father of Z. This is valid here. Y can become a father of Z. So this condition exists. Condition exists. In the earlier case, this second condition was not valid at all, right? Y becoming a wife of Z, that second condition is not at all existing. It's not valid. That's why in the earlier case it was transitive. In this case it is transitive, but in this case it is not transitive. So with this, we've come to the end of this particular topic. We will solve some more problems in the next video. Thanks for watching. If you like this video, do press a like and share it. Thank you.